Welcome to After Hours Engineering, Update Plus. I didn't want to wait too long to start the next series, so I decided to kick off this series by covering an itinerary for what the next adventure is going to be, and it is both an update and an introduction. First, I've given the processor a name, Ranger RISC. It's not the fastest chip on the block, but it does implement the ISA, and as such, I'd like to clarify a few things by saying, understand that this RISC-V is an ISA specification. It is not an implementation specification. You are free to do whatever you want in order to implement the ISA. 2, this is an educational variant of the RISC-V processor. It's not meant to be anything but that. You can use this as a way to understand a single cycle processor or a pipeline version of it. This will give you an idea of how a RISC-V processor works. It is first and foremost a multi-cycle variant, to the point where I've added extra cycles that you normally wouldn't add in an instruction, just to make it really clear where the setup and hold times are when data is moving around the data path. The focus is on understanding the implementation and not the performance. There are countless number of pipelined and single cycle versions that are considerably faster, like 2 orders of magnitude faster. Now, having said that, let's take a look at the itinerary on what's coming up in the new series. We begin by looking at the simulation, and by that I mean we're going to look at the makefile first. It's a very simple makefile. It's structured so that it's easy to understand. The goal here isn't about makefile systems, it's about RISC-V. So the intent is to keep things focused on the microprocessor itself. Then we'll take a look at Verilator. That is the simulator we will be using this time rather than iVerilog that we used in the previous series. Verilator has a very strong linting mechanism built into it, and we'll take a look at that, and we'll use a simple mux to work our way through the Verilator and all of the things that you can do with it, at least focused on the processor itself. There are a lot of things you can do with Verilator. We're going to be using a fairly small subset of it. Next, we'll look at System Verilog. We're going to focus just on basic usage. We'll use the logic statement instead of wired or register. We'll look at using type enumerations, the always combinational, and always flip-flop statements. In addition, we're going to skip some of the toolchain features, more like their advanced usage. For example, performance, timing, layout, or registering I/O on pins. We're going to skip those things and focus squarely on the processor itself. Then we'll look at the components themselves, and we'll begin by looking at a monolithic design like the Cayenne RISC-V versus a modular design, the Ranger RISC. Our modular design uses 5 basic components: mux, register, register file, memory, and a control matrix. We've seen these before in the A09, but now we're going to adapt them to the new framework with System Verilog and Verilator. We'll then start diving into the RISC-V concepts itself. For example, byte and word addressing and how it abstracts the physical memory layout. We'll look at the instruction building from produced to the instruction itself. For example, I call it bit swizzling. You have the immediate branching, jumping, load, store. There's a whole host of concepts and underlying features of the RISC-V processor that we'll go through as we implement them on the FPGA, or in this case, simulation starting off. And finally, we'll look at synthesis and what extra components we need to add in order to support visualizing the softcore running on the target device. How long it takes to complete our journey is anyone's guess. Since the last update, I finished building the modules and I'm now building the control matrix to handle all the instructions. So far, I have the I type, the S type, and the R type. The I and the S are core to the RISC-V processor because it is a load store concept. Things are working well, getting used to Verilator and a bit of work, but it is actually manageable and easy to use. I'm ready to start the series, and in the first episode, we'll put together a verilator simulation using multiplexers as an easy entry point. So until next time, peace.